Welcome. Today's lesson is entitled Angles, Degrees, and Introduction to Radians. As you can probably tell based on the title, we'll continue our discussion dealing with the degree unit of measuring angles, and then set the stage for a different unit of measuring angles, something called radians. It would actually be great if you could get a flexible ruler and a compass for this particular lesson, as we'll take a look at an investigation on the back side of your notes worksheet. And in that investigation, I'm going to have you probably construct a circle and try to measure around a circle. So again, if you can have those tools, it would kind of be nice to help out with that piece. In the meantime, though, why don't we go ahead and hit the front side of your paper and the investigation at the top, and just continue a little bit more with the degrees. So the investigation reads, what is the degree measurement of an angle with a rotation of 1/720th counterclockwise? And as you may recall from the previous lesson, we saw a nice correlation between the amount of a rotation in an angle and the degree measurement of the angle. And so we'll go ahead and take a look at the exact same piece here today. So just a review, nothing more. So I have 1/720th of a rotation. And if I want to essentially convert that into degrees, I'm going to use what is called dimensional analysis to do that. And I'm going to use the fact that 360 degrees is one rotation counterclockwise. And so this allows us to change the units without changing the value. And as we of course saw, the rotations will cancel out, and my units will be the degrees that you see right here. So let's just get this numerically, of course. And just dealing with the fractions here, not too bad. 1 times 360 is 360. 720 times 1 is 720. And so that's the amount of a degree that I have. And in this case, I did pick this for a very particular reason. This actually, if I went further and reduced this reduces beautifully into just 1/2. So essentially, I do have half of a degree. And I'm just going to write it like this for the time being, and then we'll kind of move on to the next piece. But that's pretty much it. 1/720th of a rotation counterclockwise would be half of a degree. What makes this one different than what we saw yesterday on the previous notes worksheet, as all the ones yesterday landed on, all the rotations I should say, landed on degree increments. 315 degrees, 240 degrees, 90 degrees, whatever the case may be. We didn't see any rotations land in between a degree, like this one. This rotation is in between the 0 and 1st degree. And so what we want to do is just find a couple different ways to represent those rotations that do land in between degree increments like this one right up here. So let's go ahead and just underline a couple things. This is what we're looking for. So rotations in between degree increments can be represented by using decimals. And by the way, that's just what naturally happened right up here, 0.5 degrees. However, we can also use subdivisions, and that's this piece right here, subdivisions of a degree. And so I kind of wrote this on your paper here. That was awfully nice of me. So why don't we go ahead and just box that up, and we'll kind of talk quickly about those subdivisions and then apply it to a couple examples. So what we're going to do is take the fact that in between degree increments, we're going to have subdivisions called minutes and seconds. And these would be the notations for each piece. So 1 minute is a fraction of a degree. Specifically, 1 minute is 1/60th of a degree. And another way to think about that is that there are 60-minute increments making up 1 degree. The next piece that I see down here, of course, is 1 second. So on further subdivision, so this would be in between the minute increments. So 1 second is a fraction of a minute, again, specifically 1/60th of a minute. Or another way to kind of think of it is there's 60-second increments in between each degree. Okay, so again, we're going to use the subdivisions here to go ahead and represent those rotations that fall in between our degree increments here. So 1 minute is a 60th of a degree, and 1 second would be a 60th of a minute. All right. So let's just kind of get used to how it's written and then do a couple conversions on that. Really, the math is not too bad on this piece. So an angle reading 45 degrees, 20 minutes, and 10 seconds. So here we have an angle in between the 45th and 46th degree increment, and this is how we're going to write it. So 45 degrees, I saw 20 minutes, let's put that in, and then 10 seconds. Excellent. So we've got our three components, 45 degrees, 20 minutes, 10 seconds. And so the two examples that I have for you that deal with this particular situation is just the conversion back and forth. So we'll first go degrees, minutes, and seconds, like you see here. We're going to convert that into decimal degree. And then if you look down at example 2, we'll switch it up and go decimal degree to degrees, minutes, and seconds. Again, the math really shouldn't be too bad for us. So I'm going to do 1A with you and then ask you to probably try out 1B. So 1A, I have a rotation that is in between the 50th and 51st degree increment, and it reads 50 degrees, 12 minutes, 28 seconds. So what would that look like in terms of decimal degree? Well, let's see how many degrees we essentially have, and that's the idea, is changing all of this to degrees. Well, of course, I have 50 degrees, so we want to have that as our foundation. But then I'm going to add the 12 minutes. And so the question, of course, is how many degrees does this 12 minutes make up? And this is at least how I think of it, and you can go off it however you want, but essentially each minute, I'll just go off of this piece, each minute is a 60th of a degree. And I happen to have 12 of those minutes. So if every minute is a 60th of a degree and I have 12, then very simply, everybody, I have 12 60ths of a degree. And that's what I want to add. So I have 50 degrees and then 12 60ths of a degree. So I'm going to add those. And then I have to add the number of degrees that come from the 28 seconds. Now just be a little careful with this piece. So watch this in action. It's kind of cool, but each second is a 60th of a minute. And each of those minutes is a 60th of a degree. So in reality here, with this second, I have a 60th of a 60th of a degree. Hope that rings true. So by the way, just as we're going to do this, a 60th of a 60th, well, as it turns out on the denominator, everybody, 60 times 60 is 3,600. So in reality, and if you want to go ahead and put it over here, it's not such a bad idea, but 1 second is a 60th of a 60th, or 1/3,600th of a degree. So if you want to write that in, that's fine. If you don't, no big deal. Well, I happen to have 28 seconds, so what that means is each of those seconds is 1/3,600th of a degree, so I have 28 3,600ths of a degree. Again, just real quick, a second is a 60th of a 60th of a degree. Cool. Well, we just kind of let the calculator take over here, and so I'm going to go ahead and bring up the calculator and get that piece going. So let's see, do that, and let's see what we've got going on here. So I'll take my 50, I'm going to add the 12 60ths to it, and then I'll add the 28, and again, just careful with the denominator. That's probably the only piece that would cause any concern, but that would be it right there. So I have, if we round, and I'm going to go to 3 decimal places on this, about 50.208 degrees. So roughly, and again, it wasn't exact, but I have 50 and 208 thousandths of a degree. Degrees, minutes, seconds, decimal degree, 50.208. Great. Would love for you to try to take letter B. Take a moment, 74 degrees, 6 minutes, and 21 seconds. What would that look like in decimal degree? Okay, well here's what I did. Just following the same idea as example 1A. Basically 6 minutes means I have 6 60ths of a degree. So just 6/60 there. And I'm going to add the 21 seconds. Each of those seconds is 1/3,600th, and I have 21 of those seconds. And so as a result, I'm just going to go add all of those degree components together, And again, I'm in between the 74th and 75th degree. And without too much issue here, hopefully, let's do the 6 divided by 60 and 21 over the 3600. Okay, I think I've got that ready to go. And that looks all right. So again, I'm going to round to 3 decimal places. I have 74.10, and it looks like I think I saw a 6 on that, and degrees. Really nice. So DMS to DD. Cool. Let's switch it up. Example 2 obviously then just reverses the process. I've given you the decimal degree, and we're going to go degrees, minutes, and seconds on this. So I'll do 2A. Would love for you to do 2B if possible. So 2A is in between the 35th and 36th degree, and I have really 437 thousandths of a degree. I guess that's how we would read this. How would that translate into the number of minutes? And again, there are 60 minutes for every degree. And then how would that relate to the number of seconds? Remember, there are 60 seconds for every minute. And that's exactly what I'm going to do. Obviously, I've got the 35 degrees. We're going to leave that as it is. It's this that I'm focused on. And so the idea, again, not really too bad, is I have at this stage 0.437 degrees, and I want to see how many minutes that would be. Well, as we started this lesson, let's do the continuation here. Very simply, it's just dimensional analysis. If I want to go degrees to minutes, I'm just going to use this idea right here. There are 60 minutes for every single degree. So degrees and minutes, here is a nice little segue from one to the other, and let's make it happen. So 60 minutes is exactly 1 degree. And now if you notice, just in terms of the units, degrees would cancel if you want to go ahead and slash those on your paper. And I'm just going to get 0.437 times 60, and that would give me the number of minutes. And so let's go ahead and do that, 0.437 times the 60. And so at this stage, I have 26.22 minutes. So if I write this completely at this point in time, it would be 35 degrees and 26.22 minutes. As you can see, this particular rotation ended up in between the 26th and 27th minute. Well, what I want to know is then how many seconds would this translate to right here? This is what's left over, and so how many seconds would that be? Well, again, guys, it's all just dimensional analysis. So I have 0.22 minutes. I'm going to multiply by a particular fraction here. Let me go back one screen really super fast. And hey, I'm just going to use this concept right here. Dimensional analysis, of course. Minutes and seconds, everybody. Here we go. 60 seconds is equivalent to 1 minute. So as I do that piece, I want to convert to seconds coming from minutes, and that's probably what it's going to look like. And so in this case, minutes will cancel. I'm left with seconds, and let's go for it. I'll bring up my calculator, and I've got 0.22 times the 60 seconds, and that'll give me 13.2 seconds. Now, if you want to go ahead and write that when we do our final answer, if you want to leave it right here, there aren't any further increments. So in between the 13th and 14th second, you can leave it like this. I use my GPS a lot, and it just really rounds to the nearest second. So that's how I'm going to do it here. And so what this would eventually read as a final answer, we've got 35 degrees. I have my 26 minutes. And then rounding to the nearest second, 13 seconds. So again, this would be a satisfactory, answer as far as I'm concerned. Okay? Hey, it'd be great if you could do example 2B. Take a moment and pull that off. Again, I've got 21 degrees, and I also have this 0.256 degrees. What would that 0.256 degrees translate to in terms of the number of minutes and the number of seconds? So subdivisions of degrees and subdivisions of minutes. All right. Well, let's see how you did. 0.256 degrees. Again, just really nice and quick on that. 60 minutes is 1 degree. I'm going to go ahead and do my 0.256. And if you've got this going, you can go ahead and just go on to the next piece. Looks like I have 15.36 minutes. So 15.36 minutes. So we're in between the 15th minute and 16th minute. So how many seconds would this translate to right there? So 0.36 is what I'm after in terms of the number of minutes, and I want to convert that to seconds. 60 seconds, 1 minute. And so one more time, I'll grab the calculator. 0.36 times the 60, and it looks like 21.6 seconds would do. I'm going to write that right here just for a moment. And if you want to go ahead and round to the nearest second, this would be, as a final answer, 21 degrees, 15 minutes, and up to 22 seconds. Awesome. Perfect. All right. Well, that would be the math going from one to the other, degrees, minutes, and seconds, and decimal degree. Let's see if we have a little room here to move on to the next piece. So we talked a lot about angle rotations, and so one idea that comes up is the concept of coterminal angles. So I'm going to go ahead and give you a little definition for this. And as a matter of fact, let's see, I'll find some room. So here's what I have. Let's get this in and then do some drawings and see what you guys think. So coterminal angles are going to be angles with terminal sides in the same position So this is going to be intriguing. A couple angles, or as many angles as we can draw, that are in the exact same position, but they have different angle measurements. So how can that be? What would that look like? Well, let's figure that out. So see if you can get that in the space that I provided on your notes worksheet, and then we'll go ahead and do a little drawing here. Looks like I have an investigation to kind of play this out, and then I'm sure an example to kind of back it up. Okay, well, let's see what we have. The investigation states, draw 4 coordinate planes. Okay, might as well start with that. So 4 coordinate planes, everyone side by side should do. Does not have to be perfect by any means, but get them in there for me. All right, looks good. Then draw an initial side and terminal side that are identical in each of the 4 coordinate planes. Interesting, okay. So let's go initial side. I'm going to do initial sides on all 4 of them just to get it rolling. So standard position, of course. So I have my initial side of the angle, and then the terminal side identical in each of the 4. Now you guys can draw this wherever you'd like. I'm just going to draw it up there. And it doesn't have to be perfect. I think the idea will come across no matter what. But basically try to draw a terminal side in the exact same spot that you did in the first coordinate plane. So something like that. And then it says, the final sentence here, use rotations to show 4 different angle measurements. All right, so if you remember, yesterday we talked about an angle measurement is based on 2 things, the direction of the rotation and the amount of the rotation. And so even though I have terminal sides in the same spot, theoretically there are an infinite number of ways to rotate from initial side to terminal side. So you guys can do this however you want. I'm just going to start with probably the most basic. Counterclockwise from there to there. That would be a particular angle measurement based on the rotation. Okay, another one, maybe instead of going counterclockwise, let's go clockwise. So even though the angle is in the exact same spot, I hope you would all agree that this angle measurement would be certainly different than this one. First of all, this is positive and that's negative. Secondly, that rotation's small, this one's larger, so numerically this one's going to be bigger than this. So again, different angle measurement. And again, you can do this however you want. How about if you went more than once counterclockwise? How about if you went more than once clockwise? Something like that. Hate to state the obvious, but can't we just continue to do this forever and ever and ever? Just keep going counterclockwise as many times as possible and clockwise as many times as possible to rotate from initial to terminal? Sure. So are there an infinite number of ways to do this? Absolutely. So those are what are called coterminal angles. In fact, here would be 4 coterminal angles, as you see. I put just a little dot, dot, dot here just to emphasize the fact that we could keep going and going and going. 4 is totally just an arbitrary number, just to get the idea. Cool. So let's talk about numerically what that would look like. And hopefully you started to see the idea that really the difference for each of those coterminal angles is just based on full rotations. And full rotations, of course, would represent 360 degrees. So what I have on my paper just for this next piece, and I'll keep it straightforward and simple, is all coterminal angles differ by multiples of 360. And maybe we'll see this a little more concretely with the next example that's on your paper. So all coterminal angles differ by multiples of 360 degrees. All right, so let's go ahead and draw a 110 degree angle. Again, fairly arbitrary here, but I think it should suffice. Easy to do numerically. Then draw and find 4, again, arbitrary on that piece. Theoretically, we could just keep going forever and ever and drawing coterminal angles. But that's what we have for. All right, so how about this? Just kind of getting the ball rolling here. How about give me 5 coordinate planes, if you would. 1 for the first, and then 4 more. Something like that would do. All right, and then 110 degrees. There's my initial side. 110 is definitely going to be a quadrant 2 angle, counterclockwise just from there to there. So everyone throw in 110 degrees on that. Okay, now here's what I'll ask. Let's at least draw the coterminal angles to the 110. So I'm going to do it as 4 initial sides, and let's go get 4 terminal sides. All right, so let's see what we want to do here. So what I want in this particular diagram is a rotation that's different than 110, and then finally what would be the angle measure after the fact. Okay, well, I think counterclockwise is probably the easiest way to pull this off first, if that's okay with you. So 110 would be from there to there. What happens if I go around 1 more time after the 110? So if you kind of break this down, here's 110, and then here's another 360 degrees because that's another rotation, and that's what I talked about up here. So bottom line, again, not too difficult in terms of the math. It looks like I've got 110 plus the 360. And let's put some degree marks on that. And if it's okay with you, I'm going to put a little 1 on the back because I just rotated once more counterclockwise on that. And you'll see why just in the next diagram. Okay, well, if I do the math right here, it looks like 470 degrees. So 470 degrees is a coterminal angle to 110 degrees. Cool. Let's do another counterclockwise. So there's 1, here's 2. Let's see if I have it complete. Yeah, it looks pretty good to me. So let's break it down, if that's all right. Check it out. I've got 110 from here to here. There's 110. Then I went around 1 more, full rotation, so there's 1 360. Then I went around another 360, so I went around 2 more 360s after the initial 110. Everyone see that? So as you can see, just bottom line is I can just, if I'm going counterclockwise, keep adding 360 degrees and get as many coterminal angles as I want. So 110 plus 360 degrees times 2, or 720 for that matter, and that would give me 830 degrees. So here's a coterminal angle to 110. All right, well, let's take a look at maybe a clockwise rotation. How about that one? That's obviously going to be coterminal to the 110. And I'm not sure how we want to play it out here. I'm not going to draw it in, but hopefully you can see it anyway. Here's 110, right? But basically what I did is then, after I went 110, I went back clockwise 360 degrees. That would be the math that goes into that. So in essence, I'm subtracting 360 degrees because I'm going clockwise 360 degrees. And I'm going to put a little 1 there because it looked like I went 1 rotation clockwise. So again, here's 110 from here to here. But then to get this angle, I took away the 360 degrees. And that would give me this piece right in there. Well, long story short, and you probably were able to think about this regardless, negative 250 would do. Let's get that last one going if that's all right. So clockwise, let's go one more. And just not to belabor the point too much here, here's the 110, and then I want clockwise twice back around to get that. So 110, and then minus 360 times 2. And so you can see, when all said and done, however many coterminal angles I ask you for, you could just keep adding and subtracting 360 degrees to your heart's content. So I've got negative 610 on that. Awesome. All right, put a little dot, dot, dot on the end there. Again, I asked for 4. Theoretically, there are an infinite number of coterminal angles for any angle in existence. And that sort of draws off what we talked about on the previous lesson. All right, degrees, I think it's run its course for the most part. What do you say we try the idea of radians? And here's our investigation. We're going to start the process with 1 radian. So here's what I'm going to ask, and hopefully you have a compass and a flexible ruler ready to go. If I can ask you to just use your compass and draw a circle, that would be great. Any size, doesn't matter. I'll just draw a freehand one, and hopefully we'll get the idea. And then this investigation, it can work in 1 circle. I like 2, actually. So if you don't mind, then just grab the compass and draw another circle right over here. Doesn't matter what size. In fact, the size of the circle tends to be irrelevant with this. But just 2 circles, however you draw them, totally cool by me. All right. So now let's grab that pencil, and I need you to locate the exact center of this particular circle right here. And I need you to grab that ruler and draw an initial side going right on through there. And if you notice, when we draw that initial side going right through there, I just incidentally created a radius. And so go ahead and put a little r right in there. Now what I need you to do, and here's where the measuring comes in, and we'll see how well you do on this. What I'm going to ask you to do is measure the length of the radius. Go metric on this if you would, as it does have some more tick marks to it and might be a little more accurate. But measure your radius. Now again, you and your colleagues probably all have different circles and hence different radii, but it doesn't matter. Measure your particular radius if you would. And here's where it gets interesting. You're going to grab that flexible ruler, everybody, and you're going to put the beginning of the ruler right here, and you are going to wrap it around the circle exactly the same distance as the radius. So for example, if this radius is 3 centimeters, what I want to do now is start here and go 3 centimeters exactly around my circle. One more time. Whatever the length of the radius is, begin right here and measure going around the circle. And then put a point on the circle so the length around that circle is equivalent to the radius. And what I want you to do is draw a terminal side right through that point. Okay, now I'm going to draw it where it potentially should be. It won't be perfect because I'm drawing freehand here, but if you did everything pretty well, should probably be somewhere around there, give or take. You shouldn't be over here, you shouldn't be over here, you shouldn't be over there. Should be somewhere in this vicinity right in there. Which means, of course, that this, what's called an arc length around the circle, is the same as the radius, and so I'm going to call it the radius. Awesome. Pretty cool. What you have just done, by the way, is you have defined and constructed 1 radian. So put a little 1 right in there for me. Cool. I think let's get the definition, and then we'll come back to exactly that piece. It'd be really nice if you can grab one of your classmates and just take a look at his or her circle and 1 radian, and I'll bet no matter what the size of the circle is, you should probably see that the terminal side is in basically the same position as yours. Nobody's should be different. And the fact that we have a uniform angle means we can have a uniform measurement for it, and that is 1 radian. Okay, let's get this in here. 1 radian is the measurement of the central angle of a circle, and that's exactly what you did there. You got that central angle of a circle. That intercepts, this is the best way for me to describe it, that intercepts an arc, and that arc, of course, has to be equal in length to the radius of the circle. And that is exactly what we had just talked about. I'll let you get that in there, and then I'll go back screen just to quickly put that together. But that is our 1 radian in a nutshell. Obviously, as you can see, quite a bit different than 1 degree. 1 degree is certainly quite a bit smaller than 1 radian. So, if you look, intercepted arc is equal to the length of the radius. And again, no matter what the size of the circle is, bigger, smaller, doesn't matter. You should have a terminal side that looks just like that. Awesome. Let's go to that next circle here and get our last couple pieces of this lesson taken care of. Everybody, if you would, use your ruler, a little terminal side right on through there. Throw a little radius for me. Now, in this case, I want you to draw a terminal side wherever you'd like. I'm just going to draw it up there for kicks. That looks fine. And what we have created is a central angle, initial side and terminal side. So there's my theta. Notice it intercepts an arc. And as you can see, just based on mine, notice the arc length is quite a bit bigger than the radius. So this is certainly not going to be 1 radian. But I'm going to label it with an S. So that's S for arc length. We'll see that a lot coming up in the near future. And it just so happens, what we want to do is be able to get a way to measure any angle in radians. And it's based on the geometric property that I'm going to write on your paper. And we'll go ahead and put that together in just a sec. All right, so let's go to that next screen. There we go. So it says on your paper, geometric property of circles. And this is one you may have seen in your geometry class. It is actually a rather obscure one, but it works so beautifully with this scenario. So here's what I have. The ratio of the arc lengths, and we'll put that together in just a second. So remember this piece, the ratio of the arc lengths is equal to the ratio of the central angles. So write that in there for me, and then let's go ahead and interpret what that means with our 2 drawings there. As I mentioned, this does work in 1 circle. I just think it's better visually in 2, and that's why I had you make the 2 side by side right there. So let me just repeat. Ratio of the arc lengths, and notice I have 2 arc lengths, so I'm going to write a ratio in just a second. Here's 1 arc length. Here's another arc length. Is equal to the ratio of the central angles. So here's 1 central angle, and here's another. 1 ratio is equal to the other ratio. Okay, so one more time. Ratio of the arc lengths is equal to the ratio of the central angles. And now we can put it together mathematically. Let's do that piece. And here is our formula. Let's put a big asterisk by it. And here's what I have. Arc lengths, guys, if you look at your two circles, S to R, that's a ratio, is equal to the ratio of the central angles. The central angles that match up would be theta to 1. And so what this basically means, and we'll go ahead and put this together in a couple different ways, our central angle in radians is very simply a ratio of its arc length to its radius. Can't emphasize that piece enough. So theta is equal to the arc length divided by the radius. We'll obviously pick this up on the next lesson, but it's good to introduce this piece. And then just put this, if you would, which means, and you see this written in a slightly different fashion, so I'm going to go ahead and do that in just a sec here. See that R, everybody, in the denominator? Well, what I'm going to do is kind of bring that up to the other side of the equation. I'm going to multiply this by R and multiply that by R, and you get a very nice simple formula that it relates all three. Again, if it's not clicking just yet, don't fret too much about it. We definitely start our next lesson based on this idea. But that is sort of what we're going to look for with radians, everybody. The measurement in radians is equal to the arc length of the circle intercepted divided by the radius of the circle. Arc length to radius. Awesome. And then just the last piece. If theta is a ratio of the arc length to the radius, as I just specified, what are the units for theta? Think about this for just a second. You probably measured on your circles in centimeters, right? So you have an arc length in centimeters. You have a radius in centimeters. What happens when I go ahead and do the ratio here, specifically the division? What happens to the centimeters, one on the top and one on the bottom? They cancel. And so when those units cancel out, you're left with really just a real number. And so here's what you're going to write, and then we'll wrap it on up. So, since the arc length and radius are the same units, they cancel out. They're gone. Slash them. And as a result, you get something that we would call a unitless measurement. And that's what you're going to have to wrap your mind around over the next couple lessons. So radians is what is called a unitless measurement. Essentially, it just comes out to be a real number. And not to be too dramatic about it, but this concept opens up an entire branch of trigonometry called the trigonometry of real numbers. Cool. Hey, we'll just pick it up on the next. If you kind of look at the title of the next notes worksheet, I'm sure it says something along the lines of radian measurements of angles. Well, thanks for listening, everybody. Let me know if you have any questions on the lesson and try out some of those practice problems.